A side project of mine recently has been automatic music generation. Specifically, I wanted to train a model on the music of Bach and see if the model could generate its own novel music in that style. I'm definitely not the first person to try doing something like this, so first I wanted to introduce some other approaches. So this is the paper for Deep Bach, which is one cool project. The title for this gives you two important points. One is that it's just trained on the chorales, which is sort of a specific subset of Bach music. They all have four voices working together. And then the other thing is it's steerable, as they call it, which just means you provide the model with a melody. It's not generating that, and then it reharmonizes that or provides an harmony for that in the style of Bach. And so it actually has a nice example based off of God Save the Queen. So another project is called the Bach Challenge. It's fairly similar in that it's also trained on chorales, and it's also basically based around reharmonization of a provided melody. So here's what the Bach outputs for Twinkle Twinkle Little Star. Nice. So those models so far were provided with a melody, and it generated the harmony. What about generating completely everything from scratch? One approach is WaveNet by Google DeepMind, which works not just for music, but for any sound because it's trained on the raw waveform, which is crazy because a waveform contains information at different levels. And so it's not easy to generate something. But here's what they got. They didn't train just on Bach, but they trained it on classical music, and this sounds almost like Rachmaninoff, I think. Now, for those of us who don't have the time or processing power to train on raw audio, a more reasonable format is to use the MIDI, which Daniel Johnson uses in his model. It's not entirely agnostic to musical structure because it seems to have an understanding of time signature built into it, but otherwise it's a bit closer to what I'm looking to do. Another model is by YouTuber Carrie KH. He trained on Bach MIDIs and I think a bit of Mozart. And interestingly, he encodes the MIDIs sort of in a text format and then runs that through basically Karpathy's LSTM model. And he gets something like this. One last example, the popular YouTuber Siraj trained on jazz music, but his model is probably closest to mine with 2 layers of LSTM. And so he gets something like this. Okay, enough background. Now to show how a MIDI format works, I'll first play a little bit of an actual recording of a Bach fugue. Now the MIDI version of the same song. So converting a MIDI file to its CSV representation of its inner workings, we get something like this. The first row just says the voice number, the track number, then this is the timestamp in the second row. So the first row is just giving you like metadata. There are 5 voices total. This is the metronome value, or just kind of the speed. But then the first voice is just other information, like if it slows down or speeds up. So really the actual voice starts with 2. So 5 minus this one voice here. So there are 4 actual voices producing notes in this file. So this is the timestamp again. The difference between these values is how long the note is held, which is this here. And then at the end is the actual pitch. This is the volume, and this, if it's not something other than 0, it's just like a different instrument playing other than the basic piano. So this goes on. So again, this is all for just that second voice, all the way from the beginning to the end of the song. And then for the third voice, and the fourth and the fifth voice, that's just later on in the file. So next I use some bespoke code to reformat this to my liking. I remove unuseful information like the header and the instrumentation. I just keep it all piano. And then I transpose all these different MIDIs so they all start in the same note. And that's maybe a little music theoretically dubious. This is what Reddit had to say about that. So yeah, my new format only records the pitch then. Here each row corresponds to a time step. You can set how fine-grained that is, and then each column corresponds to a voice. So this piece here initially begins with just one voice producing notes. If you recall, it's duh, 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 duh. And so then that's this here. You can see the pitch value changing. If we go down, we can find where the second voice joins in, right over here. Further on, the third voice, and so on, the fourth voice. Now if we reverse everything and convert this as it is back to a MIDI, this is what it sounds like. So other than slight global changes in pitch and speed, structurally it's the same song. The only thing we have to be careful about is, again, how fine-grained we make that time step. If we make it too wide, it sort of loses the smaller notes, as we can see here. So now to actually train our model, we need the input data, the X data. We'll be using a sequence length of 3, which just means it's the past 3 notes it's trained on each time. So this here, it just got 4 times 3, so 12 total in each slice of the matrix. You can see in the original format we had 50, 50, 52 starting the song off, and so then you can see the second voice here has those same values. And so we just repeat this then, incrementing by 1 time step each time, so on, and we'll feed this into our model to train it on. So now the Y, or the output component of our training data, before we had the previous 3 notes, this just shows the following single note. It's shown here as an array of size 300. The reason for that is that there are 74 different note values encountered in all the training data, plus I'm encoding silence as its own value, so that's 75 times 4 different voices. That gives us 300. Each voice has a single position turned on for that note's value, including silence again, so it's in effect a 4-hot vector. Here's the model architecture. Nothing too fancy. It's got a base plate of prefamulated amulite, 2 LSTM layers with 100 neurons each. Those hidden layers have ReLU as the activation function. At the end there's a sigmoidal activation function. And finally some dropout to prevent overfitting, so we're not just quoting existing Bach pieces, but hopefully creating new pieces in the style of Bach. So I scraped this web page that has a bunch of Bach MIDI files, fugues, chorales, all different styles, and then I limited it to pieces that have 4 or fewer voices, and if it does have fewer than 4 voices, I filled the other voices with just silence, and I trained on that. Here's what I get after training for just 1 epoch on my CPU. I thought that was pretty promising. It's got some rhythm and harmony, and if I feel bad about its imperfections, I feel better when I listen to truly random music. That's enough of that. So, now let's try listening to a piece after 10 epochs. Still not bad, I think. And so at this point, I thought if I just trained it more, I'd start getting some really cool pieces. I trained up to 300 epochs because that took a long time, and this is sort of what I got by that point. I'm not that impressed. I honestly expected better. Um, Thinking about this, one reason I think we get these kind of weird sounding chords is actually just based stuff of how I structured the predict function. So in the training data, let's say you see a C major chord. That might be followed by an F major chord. It's also not unlikely to be followed by a G major chord. But since we only predict one note at a time without knowing what's come so far, we can end up picking notes that belong to these two separate chords, G and B from G major, but A from F major. That doesn't sound as nice, or at least not as normal. So I think if I restructured my predict function, that would at least give me some easy improvements. Until I do that, change the pre-processing or change the model architecture, I'll just remind you again how much better this sounds than random notes.